So this question we did in class, and here's a video sort of walking through it a little more slowly. If you haven't started it yet, pause this video, don't look at the diagram I have in front of you, and try to draw that yourself based on the information. But what we have is a plane flies 35 kilometers in a direction 30 degrees, and this says north of east. So what that means is you start east and you swing north. So this pink arrow that I drew down there, that's 30 degrees north of east. So that first, and you always measure your angle relative to the tail of the arrow. So I put this green green like north, so this is supposed to represent the north, south, west, east of the thing, and I'm orienting my arrow so that it's pointing in the northeast quadrant, and it's east, and I've swung 30 degrees north. Then I'm going to put the tail of the second vector, the light blue one, at the tip of the first one. So I put another green north, south, east, west, north, south, west, east. And now I'm measuring 20 degrees east of north. So start north and then sweep east like that. And that's 20 degrees. And the direction, so that's 20 degrees east of north. I did this on purpose, just the north of east, east of north, to sort of get you to play around with those terms and understand them. So then that length of that arrow is 57 kilometers. So ultimately what we're looking for is this red arrow, which represents the total displacement, delta D total, of the whole trip. All right, so we're going to solve this by adding components. So what that means is we need to find the components of each individual vector and then add them together to find the component of the resultant. So let's start by drawing our components. So let's say we can draw the components of the first one and remember, they're just along the X and Y axis. So here is, let me change this to graph paper view so that we can get a good sense of the lines here. So that would be this orange vector that I've just drawn would be the X component of the first vector, and I can draw this green one. Hang on. I'll draw this green one as the Y component of the first one. And then I can also input the X and Y component of the second one. So this one is going to go to about here. And then I can put its counterpart is here. Okay, so those are the two vectors. And what we did in class is we sort of illustrated it this way. If I take this vector and lay it down here, and I add it, the X component of the first one, and I add it to the X component of the second one, and then I do the same thing for the Y's. I take the Y component of the first one and add it to the Y component of the second one. What you can see is that it gives me the X and Y components of the resultant. So you see how that works? And this is like a key to understanding this problem. Okay? So what I want to do is I want to know both of these. So I want to, let me move this over a little bit so you can see them side by side. What I want to do is find the X component of the first one, add it to the X component of the second one, and then do the same thing with the Y's. And once we do that, we'll have a value for this. And what we're looking for is to solve this delta D total. We need both the magnitude, which is the length of that arrow, and the direction theta. But once we know the lengths of these sides, we can use our tools of Pythagoras and tan inverse. All right, so I'm going to shrink this down a little and move it up so that we can set it up in terms of the X and the Y coordinates. So if I do this like this, I can say X coordinate and then Y coordinates. And what I'm going to do is set it up for each of the vectors. So let's start with the 35 kilometer vector. So I want to know what the x, I shouldn't say x coordinate, I should say component, sorry. I'm going to relabel these and say x component and y component. All right, so the x component is actually this orange arrow. So let me just put that in here. I can just say this is actually the vector I'm looking for. And the y component is going to be this thing. I can put this over here. So just as a visual reminder of what we're trying to solve for. So how do I solve for that? Well, I'm going to solve this triangle. And the triangle that I'm solving is, let's see, I can do this too. I can take these three. I can't do it. I have to. So if I take this, so to find the information for the first one, I'm going to take, oops, I want to take this one and I'm going to add, so basically it's this triangle that I'm solving here. This is found by adding these two components. Okay, so this is what I'm going to be solving. And I know the angle here is 30 degrees because that's what it says in the problem. I know this is 35 kilometers. So in order to find the x and the y components, this is the adjacent side, this is the opposite side. So if you think about it, looking at my SOHCAHTOA, so what do we know here? Well, we know that the cosine of 30 is equal to the opposite, which is, sorry, the adjacent, which is the x component, over the hypotenuse, which is 35. So to find the x component of the first vector, I'm going to say 35 cos 30. And then to find the y component of the first vector, it's just the sine, right? And I'm just going to write it out, 35 sine 30. So those are the two values I'm going to put into my little table here. I'm going to say this is equal to 35 cosine of 30, and this is equal to 35 sine of 30. Okay, and when I calculate that, I get this equals 30.3 kilometers, and this equals 17.5 kilometers. All right, done for the first one. I know my x and my y coordinates. So let's move on to the next vector, which is the 57 kilometer vector. I could do the same thing I just did. I can take this. I want to solve this triangle, right? So I'm gonna just put this triangle down here and then copy this one. I'll move it in a second so you can see it. So I'm gonna say this is an addition of this plus this. Okay, so now it's visually there so I can see it. The angle, now what is the angle? If you look at the original diagram, what I described was an angle of 20 degrees, which is up here. So this angle is 20 degrees. So then that would make this angle 70 degrees. We know this side is 57 kilometers. So we're going to solve this the same way we solved the other one. And that is by using our trig identities. And you can see from looking at this triangle, hopefully you can see this pretty quickly, that x2 in this example is 57 cosine of 70, and y2 equals 57 sine of 70. All right, and I can put those numbers in here, into my table. So 57 cosine of 70 is equal to, now if I quickly do the math in my head, I get 19.5 kilometers. If I go 57 sine 70, I get 53.6 kilometers. So now I know the values of all of these things. So, I mean, if you think about it, this is just x1 plus x2, right? And up here, we have y1 plus y2. So now what I'm going to do here is just add it all up. So I'll extend this a little bit and then just say delta I call this D. Delta D total is just going to be 30.3 plus 19.5. And the y component is going to be 17.5 plus 53.6. So when we do all that math, we get 49.8 kilometers, and then we get 71.2 kilometers. All right, now I know the components of these two. So I know this is 49.8 kilometers, and I know this is 71.2 kilometers. So I can solve this. I'm just gonna bring it all the way down here and redo it. I can just take this angle, this vector, hang on one sec. This vector, I can put it here, and then I've got these two. Well, let me just say this. I'm just gonna make it this. This plus, well, I guess I got it a bit off, this. Okay, so then what did we say our numbers were? We said they were 49.8 kilometers, and then this one was 71.2 kilometers. And this is theta. So in order to describe this vector, I need to have both the magnitude and the direction. So the magnitude, basically how big it is, magnitude, I can find using Pythagoras. So delta D total, so delta D total is equal to the square root of, I'm getting a little sloppy here, 49.8 squared plus 71.2 squared. And when you solve this, you end up with 86.9 kilometers. So that's our first, that's part of what our answer needs to be. Because we want to know the displacement, but we also need to know direction. So we need to calculate the direction. In order to do that, I'm going to solve this triangle, but I'm going to see that I know this and I know this. So in order to find theta, what I'm going to do is use those two numbers. So I can say tan theta equals opposite over adjacent, 71.2 over 49.8. So then I just take the inverse tan inverse. So theta equals tan inverse of 71.2 divided by 49.8. And when I do that, I end up with 55 degrees. So 55 degrees is just this theta, but that doesn't tell me the direction it's actually pointing. So in order to do that, I have to remember that this is like, this direction is north, this direction is east. So what I'm talking about here is east of north, right? So if I wanted to write my direction, I would say 55 degrees, north of east. Another way to write it is east 55 degrees north. They mean the same thing. These two are exactly the same, but this is part of the answer. So if I'm going to do this, if I'm going to write down the final answer, I would say the displacement was 89. Yikes. 86.9. I got that wrong. It's 86.9 kilometers. And then it would be 55 degrees north of east. So that's my final answer that I would want to record. Thanks.